Every single time an airplane takes off, something truly remarkable happens. A machine weighing hundreds of tons, packed with people, luggage, fuel, and metal, just lifts off the ground and stays in the air for hours. Most people are told a simple answer. Air moves faster over the top of the wing, creating lift. But here's the truth. That explanation alone is incomplete, and in some cases, it's actually misleading. Today, we're going deeper, not into confusing equations, but into the real physics, the hidden forces, and the engineering decisions that actually keep airplanes flying. By the end of this video, you won't just know how airplanes fly. You'll understand it in a way most people never do. Let us start with the first big myth. Lift is just Bernoulli's principle. You've probably heard this before. Air moves faster over the curved top of the wing, the pressure drops, and lift happens. This idea comes from Bernoulli's principle, and while it's partly true, it's not the whole story. Here's the key thing most explanations leave out. Air particles do not meet back up at the trailing edge of the wing. Wings do not rely on a longer path alone to create lift. In real-world flight, something much more powerful is happening. To understand it, we need to talk about momentum. The most accurate explanation of flight starts with Newton's third law. For every action, there is an equal and opposite reaction. An airplane stays in the air because its wings push air downward, and in return, the air pushes the plane upward. That's not a metaphor. That is physics. Every second a plane is flying, it is grabbing massive amounts of air, redirecting that air downward, and gaining an upward force in return. This force is called lift. So what do wings actually do to the air? This is the part that's rarely explained well. A wing isn't just a curved surface. It's a precision-shaped air deflector. When air hits the wing, some goes over the top and some goes underneath. But most importantly, the air leaving the wing is forced downward. If you could see air molecules as a plane flies, you'd notice a downward jet of air beneath the wing and a rotating airflow pattern called downwash. This downwash is direct evidence that the wing is pushing air down. And because momentum must be conserved, the air pushes the airplane up. So where does Bernoulli's principle still matter? It isn't wrong. It's just incomplete on its own. Here's how it fits in. The faster airflow over the top of the wing does create lower pressure above it, while higher pressure builds up below. This pressure difference helps stabilize the lift, but it exists because of how the wing redirects the airflow, not instead of it. In short, Bernoulli explains the pressure pattern, while Newton explains the force. Both work together, but Newton's laws are doing the heavy lifting. Now let's talk about the silent hero of flight, the angle of attack. Here's something most people don't know. Wings can generate lift even if they are completely flat. The secret is the angle of attack, which is the angle between the wing and the oncoming airflow. As long as a wing meets the air at the correct angle, air is deflected downward and lift is generated. This is why planes can fly upside down, why fighter jets use flat or sharp wings, and why aircraft don't rely on curvature alone. Curvature helps, but the angle matters more. This brings us to why airplane wings are so large. Lift depends on four main factors: the density of the air, the speed of the aircraft, the wing area, and that angle of attack. This explains why planes need long runways to get up to speed, why wings are so massive on heavy aircraft, and why planes struggle at high altitudes. At higher altitudes, the air is thinner. There are fewer air molecules, so the wings must move faster to generate the same amount of lift. That's why planes climb slowly, cruise at high speeds, and use long, efficient wings. The role of speed is critical. An airplane can't take off at just any speed. It must reach a minimum airspeed called takeoff speed. Below this speed, not enough air is being deflected, so not enough lift is generated. Once that speed is reached, lift exceeds the aircraft's weight, and the plane leaves the ground. This is also why stalls happen. In aviation, speed is life. A stall is not an engine failure. It's a loss of lift caused by insufficient airflow over the wings. This surprises many people, but engines do not lift airplanes. Engines provide thrust, which increases speed and allows the wings to do their job. Even a glider with no engine at all can stay airborne as long as it has airflow over its wings. The engine's real job is to overcome drag, maintain airspeed, and keep the lift continuous. So why don't planes just fall out of the sky? Here's a powerful truth. An airplane in the air isn't being supported by the air. It's constantly falling forward and missing the ground. As long as lift equals weight and thrust equals drag, the plane remains in steady, level flight. If the engines stop, the plane simply becomes a very efficient glider. Lift still exists, and a controlled descent is entirely possible. This is a key reason why commercial aviation is so extraordinarily safe. Here's something you might not have noticed. Wings actually change their shape during a flight. Modern wings are not fixed. They have flaps, slats, and spoilers. During takeoff, flaps and slats extend to increase the wing's surface area and curvature, boosting lift at lower speeds. During landing, spoilers are raised to increase drag and reduce lift, allowing the plane to slow down safely. Wings are dynamic machines, not static surfaces. There are also hidden airflows that make flight stable and efficient. Advanced aircraft rely on controlling wingtip vortices, managing the boundary layer of air, and designing for laminar airflow. These complex techniques reduce drag, cut fuel consumption, and smooth out turbulence. Some modern wings are even designed to delay airflow separation, maintaining smooth lift at high efficiency. This is cutting-edge aerodynamics, and it's constantly evolving. And what about turbulence? It feels scary, but structurally, it's not a major concern. Aircraft are built to flex. Their wings can bend by several meters safely, absorbing forces instead of resisting them. Turbulence is uncomfortable, but it's not dangerous to the integrity of the plane. Ultimately, the reason flight feels like magic is because humans evolved to move on the ground. But in reality, air behaves like a fluid, wings are tools for interacting with that fluid, and flight is just a form of controlled momentum exchange. There is no magic, only precision physics. So let's review what you now know that most people don't. Airplanes stay in the air not because air travels faster on top, not just because wings are curved, and not because engines push them up. They stay in the air because wings redirect massive volumes of air downward. Momentum is conserved, pressure differences stabilize the lift, and speed and angle are carefully controlled. You now understand flight at a deeper level than most passengers ever will. If this explanation finally made flight make sense, please like this video and share it with someone who loves learning. Comment with an airplane emoji if this changed how you see flying. And be sure to subscribe for more deep, simple explanations of how the world works. Thanks for watching, and thank you for being curious.